Hi everyone. Today we have the pleasure of hearing from Dr. Aaron. Aaron will be presenting on defining what's normal, the basics of database normalization.
All right, thank you. Appreciate it, Diana. So today, as mentioned, we're going to be talking about database normalization, and so that we can help define what is normal. So to help you get started, first of all, I'm going to discuss, um, get my presentation going here. Going to discuss the just who I am. So my name was SQL RV, and I am known on the internet as such. I do go around in the United States in a recreational vehicle. Currently, I have a motorhome, and I give presentations related to SQL, anything related to databases. Uh, I am the current Director of Data Services at Honest Health, and I have also been affiliated with Redgate and also with Synchrony as an advisor for them. And I've presented at a few conferences, as you can see, at various times throughout the last many years. I got a Bachelor of Science in Computer Science at Ball State University and a Master's of Science in Computer Information Systems from University of Phoenix. However, when I switched into healthcare, I went back and got a Master's in Health Informatics because I learned that I could really do some work on cool projects to help save lives. And I continued on and got my doctorate in healthcare administration. So as you can imagine, I've been doing this for quite a few years. So today, we're going to be talking about database normalization, its use cases, the goals that we have for database normalization, and then we're going to talk about the normal forms. And these are, we'll get into that a bit more later, what that means. Then we'll also touch on what denormalization is and some of the reasons why we would want to denormalize and the methods that are behind such denormalization. And also there are some drawbacks that we want to talk about before we look into denormalization. Then we'll wrap with a few closing thoughts. So something to consider is what Edgar Frank, or also known as Ted Codd, wrote. He said, every non-key attribute must provide a fact about the key, the whole key, and nothing but the key. And this is kind of a play on in legal precedents where they say, well, they want the truth, the whole truth, and nothing but the truth. And so I think that was quite appropriate. In database normalization, why would we want to normalize? Mainly it's because we want to reduce the data volume for inserts and updates, because otherwise it would become very complex. And because of that complexity, it would also introduce anomalies and errors in the data. So we want to reduce that as well. And by doing that, we improve the data integrity as we go through these steps. So let's consider some use cases. For example, in highly transactional systems, you want data to be going in and out very fast, and you want to keep the amount of data being processed to small amounts so that you can do things quickly. We also have to consider where space is a consideration because you may not be able to have unlimited storage available to you. Now, in today's world, it's probably not as important because, as they always say, disk space is cheap. But that's not always the case, and disk space is not always the only consideration because you may have network bandwidth as well to consider. Situations where the width of rows is a problem. In I should say in highly denormalized data environments, such as a data warehouse, the rows for a table can be considered quite wide. That's because you've got a lot of columns in it. But in a transactional environment, you want to keep that fairly narrow, again, because it helps improve your performance. So the first normal form that we're talking about, and basically when we talk about a normal form, we're talking about a set of rules for a normal form. So in this first normal form, the first rule is every column in the table must be unique. So that means you do not want to use multiple fields in a single table to store the same data. And yet we see this a lot in our environments where we have email 1, email 2, or we have phone 1, phone 2, or something of that nature. The problem is that it doesn't help delineate the data well enough. It doesn't make it distinct enough. And you could also run into problems if you allow for, say, up to 3 different email addresses. What if somebody has a fourth or a fifth and that you need to add? So it causes problems with that. And this holds true even if the column names show their purpose, such as a work phone or cell phone. Now, we do it all the time when we're expecting only, 1 or 2 types. But when there are multiples, or there could be a situation for multiple that are significant, then it becomes a problem. It also doesn't allow for new types. So, for example, if we have only work phone and cell phone, what if we want to have something else such as a spouse phone or something of that nature, or whatever the circumstances may require? And so you would have to add another column to the table, modify the database, modify all the processes that interact with it, just to allow for that additional phone. And that becomes a lot of work to accommodate. The second rule is that separate tables must be created for each set of related data. So in other words, if I were to have the emails and the phones separated, I would want to put that into another table. And so I do that by creating a contact table, and then I have an email table and a phone table so that I can have multiple values for each of those different types. And it allows for a variable number of values. And so if I have 3 of them in for a particular record, I add a fourth one, there is no change to the data structure at all. I also want to be able to group related columns together. And so if I have like email address and email type, I want to keep those together into that logical grouping because it just helps to make the data more sensible. The third rule is that each table must be identified by a unique primary key. This kind of goes back to what Cod was saying about the primary key is the whole key and nothing but the key, because that primary key uniquely identifies that particular record. You don't want to have a situation where you have, I have a primary key plus something else. And so because the primary key is supposed to be that unique identifier for each row. And the primary key can consist of 1 or more columns. It's true. It can be a natural key. So if I have a record that says I want last name and first name, and those 2 together must be unique, that's okay. That's still considered a primary key. But in most cases, what we end up doing is we create what's known as a surrogate key. And so we'll create some sort of identifier for that record so that there's only 1 key field for that particular record. And I believe, at least in the practices that I've used, that has been the most common and the most preferred. The fourth rule is that no rows may be duplicated. So in other words, each row should be unique. You don't want to allow the same data or the same record completely to be entered in multiple times. For one, it would violate the primary key. And the other is that if you allowed that, then it could cause further problems. If you have multiple columns that repeat the same data, that's probably screaming for you to move that into another table. Rule 5 is that no columns may be duplicated. So you don't want to store the same thing in multiple columns. So if I have, say, a primary phone and secondary phone, and they both have the same phone number, then that becomes confusing. And that's another reason why we don't want to have, multiple columns of the same purpose in the table. Oh, and I should mention also that you want to make sure that if the columns repeat in multiple rows and they become redundant, that's an indication that you can separate that out as well. The sixth rule is that no row or column intersections contain a null. Now, this one I would have to say is more of a guideline. This was something that Cod felt very strongly about. He did not like to store null values in a database. He felt that everything should have a value. However, in practical circumstances, a null really represents that there is no known value. And in most databases, such as SQL Server, Postgres, and Oracle, they allow for a null value in a field to represent that there is no known data for that. But some circumstances don't require that or don't allow that. So we want to be mindful of that. In those circumstances, they require a default value. So say, for example, if on a phone number, if we don't know what a phone number is, you may be able to get away with putting a 0 for the phone number, assuming that you're storing only digits. Or if it was a text field, you could put no known phone number or something of that nature. But that's not always the case. For example, in a quantity field, if I were to put quantity of 0, that could be significant and would have a different value than an unknown quantity. So again, because of that, it's not practical for most database implementations to enforce a no null constraint. Their seventh rule is that no row or column intersection contains multi-valued fields. And this can be exemplified by those that have comma-separated lists in a value. If you were putting into a field, value 1, comma, value 2, comma, value 3, then that screams that you need to put that into a separate table. Because you want only one value per column in a row. So again, for the example, email, for example, if we were to have primary and secondary, separated by commas, that just tells us that we can have multiple values and it should be in a separate table. Because we really want to have discrete values in one field in a record. So here's an example of a first normal form table where we're transforming to a first normal form. And so here is a contact information. And we have in here our first name, last name, work number, cell number, email 1, and email 2. As you can tell, this already violates the first normal form rules that we talked about. So let's go ahead and break that out into some separate tables. First of all, we would have our contact table. And this consists of an ID and a first name and last name. And then we would create, and we map those into that table. And then we create another table for the phone, and we map the values into that. Notice that we have multiple rows per person because we can have a work phone and a cell phone. And same thing, of course, with the email, and we map that in as well. Now, this isn't really the best way to do it yet, even then. So we have what's known as the second normal form. And the first rule for that one is to create separate tables for sets of values that apply to multiple records. So for example, when we talked about the phone types and email types, so we would want to separate that out. So we have a table for phone type, one for email type, so that we can apply them to multiple rows and even multiple tables. The thing is that it ensures that we have consistent usage and consistent values in each of the times that they are used. And it helps us to maintain data in that primary key definition so it's specific to that key. The second rule is that we want to associate related tables through a foreign key. And this is where we get into referential integrity between tables. So a foreign key is really, you can think of it as a stored reference to some other table's primary key. And so it points to another row in another table. So a contact ID in the table phone then references the contact ID in table contact. It gives us that pointer backwards. And it ensures that in our rows, we have one table with corresponding rows in another. This is that referential constraint that we talked about. We also want to make sure that a foreign key doesn't have this, a foreign key is not required to be unique because it multiple rows can point to the same record of a primary key in another table. So it doesn't have that same requirement that primary keys do. And it's also possible that a foreign key could be null, because if there is, say, for example, no phone number for a particular contact, then of course that foreign key reference would be null, because it says that this person does not have any phone number. So let's take a look at that example. Remember, we broke out the contact into phone and email tables. Well, we're going to refine this a little bit further. So now I'm going to take the contact, and it's pretty much the same, but notice the phone table that we modified it. We've added an identifier in here for the phone ID itself, just like what we had here before, but now we have our foreign key reference back to the contact for which that record belongs. So this contact ID number 1 says it's the primary key in the contact ID table. And then we did the same thing for the email, where we broke that out so that here, for example, contact ID 2 as a foreign key back to the contact ID, primary key number 2. But we can still do better. So let's take a look at the third normal form. And the first rule of that one says we want to eliminate fields that do not depend on the primary key. For example, if we're storing data in a record and it has nothing to do with that primary key whatsoever, it doesn't belong in that record. So we want to make sure that we put that into someplace else so that it can have its own unique primary key. We also want to make sure that we don't store the data that's better suited in another table. So when we talked about the phone type and email type values, those should really be defined in their own tables. Now, I want to throw a caveat in here, and this is something to consider, is that as we go through and we keep refining this normalization to get down to more and more granular data, sometimes we run into performance issues and we want to back off from that normalization. And I'll talk more about that in the denormalization process. But performance comes into play in here, and so we want to balance that requirement. So for example, in third normal form, as we started from the second form, we're going to bring down our contact table, and notice that in our phone table, instead of referencing the phone type by a name, we put that to a separate table with an identifier. This gives us the added benefit of the fact that if I were to type something in here and I spelled it as WROK because I was typing in a hurry, then I wouldn't have an unknown value in there that doesn't fit. And so this forces us to have discrete values in there for that type. And we did the same thing here for the email table, but I didn't have room on the screen to show you that table as well. So it would be table email type, and it's broken out into work and personal. Now, there are some additional normalization forms, and I'm just going to run through these briefly because most of the time they're not really used. For example, the voice cod normal form, they sometimes called it 3.5 because it came in just shortly thereafter. And again, just iterates that we don't want to have any more than one candidate key. Fourth normal form, again, further redefined to say that no table contains two or more independent and multi-valued data, which we kind of covered in the second normal form. And fifth normal form said that we can't break a table down into any number of smaller tables. And that's just more of a statement, again, of the third normal form. Sixth normal form hasn't even been well defined. It was proposed, but no one's come to a consensus on what that one should be. So I wouldn't even worry about that. So again, just to give you an overview of what database normalization is, it can be summarized into one sentence exactly. And so it's the key, the whole key, and nothing but the key, so help me COD. All right, so let's take another look at why we want to do normalization. First of all, is to reduce data redundancy. As I mentioned, we don't want to store the same data in multiple places because then you reduce your single source of truth. You want to reduce your data discrepancies. Again, if you have data in multiple places, it could be right in one place and wrong in another, and you won't know which one is correct. So you want to provide a single source of truth for that and improve your data integrity. Now, again, as with every rule, there are exceptions. And so we want to consider the fact that if you have too many small tables, you can hinder performance. Because if you have every one of your queries has probably half a dozen or more joins in there just because of these small tables, that can hinder your performance. It can also increase your complexity. And if you increase the complexity too much, then you increase the risk of something going wrong. So you want to keep the application purpose in mind. Or as another way that I've seen before, like the Dalai Lama said, know the rules well so you can break them effectively. And then this is where we come into database denormalization. I'm a big fan of various comedy skits, and one of my favorite was Young Frankenstein. And so when we talk about normalization, then we talk about what is considered abnormal, or as they put it, abnormal. So denormalization is really where you want to optimize for data reads. Normalization is great for being able to update data because it helps you to ensure that you have one source of truth for that data and the records are small, so they're updated rather quickly. But when you go to do reads, and if you have complicated queries to be able to do those reads, then it becomes more problematic. And so sometimes keeping data duplicates reduces the number of tables in our queries. And as long as the data is not being used for transactional purposes, then you're okay doing some denormalization. So in other words, a great use cases for that is for a data warehouse where you're doing reports and analytics. Now, normalization is important and it should be followed first. Because again, like I said, it's critical for data entry and processing. So denormalization should only be followed under careful and strict circumstances. So let's look at some of those reasons for denormalization. First of all, let's say that you're wanting to maintain some history. Now, I could store historical changes to data. And if I do it, say, in a time-based records in the same table, I could do that. Many database platforms allow for some sort of historical data management within the same table. Or I could even create a separate table just for historical data so that I can go to it only when I need to. You also want to be able to perhaps reproduce data as of a given date. So let's say I'm going to know what did this record look like at the end of last month, and I could give a date for that particular record and look at it as it was then, not necessarily how it is now. We'll also want to be able to enhance our query performance because we wanted to be able to reduce the number of joins used in our queries. This is really helpful for being able to look at rarely used data as we go through our lookups, et cetera. And we want to be able to combine often used queries into a fixed result set to, again, reduce our time in our lookup. We also want to be able to accelerate our reporting. We can pre-aggregate data. We can look at a number of averages and statistics. We can reduce the impact on our source systems by having data in a separate environment. And we can provide for multiple users concurrently with lower costs. It helps us to simplify data management so that we can pre-calculate values to avoid on-the-fly calculations to reduce system impact. We can avoid logic from being implemented in multiple places by having it done once and then transform and store it in that way. And we can reduce or eliminate complex data manipulations by doing that in our ETL process. And we can store data that's normally derived at runtime, and so that we can access it more frequently. We can pre-join data together. so that we can simplify those queries and store or look up our reference values to make that even quicker as we go through. We have some use cases where we may want to keep details in a master record, or we may want to keep detail or master values in a detail record so that we don't always have to keep looking them up all the time. Now, there are some drawbacks. Of course, one of them is that we're going to have extra storage for this data. And if storage is cheap, then that's probably not a problem. We also have to maintain our documentation to show that, where these transformations were occurring, and that's usually also not a problem. We want to be careful of potential data anomalies and make sure that if data becomes out of sync, it could impact our reliability. So we want to make sure that that synchronization is up to date. And of course, there's going to be additional code for some of those ETL logics. And it will slow down inserts and updates. So we don't want to use that for transactional purposes, but again, only for data reading purposes. So for example, name parts. Name parts is a good example. Technically, we should have a table that has every name part as a separate row, but we never do that. We always carry last name, first name with separate columns because that's a common usage. It doesn't fit all scenarios, but again, it's the most common. Same thing with address. We don't store address line 1 and address line 2 in separate rows of a table. We store them in separate columns. So these are common denormalizations that we do each and every day. So we talked about data normalization, its use cases and its goals. We discussed the various normal forms and denormalization, why we would want to do it, how we could do it, and some of the drawbacks. So some things to think about is that most tables should be at least second normal form. And while it's desirable to have things as third normal form, it may not always be practical. So we want to strike that balance between normalization and denormalization. I like to say that we should design with normalization first in mind. Now, we do want to keep a proper mind on performance and understand what that logical design is, and focus only on the parts that really need help. Take a look at the performance issues and fine-tune your queries first before you start denormalizing your data. Trial and error is going to be your guide as you gain experience in what your data situation calls for. Every situation is different. But the only rule of thumb that I like to apply is that normalize until it hurts and then denormalize until it works. So in the slides that you'll have available to you, there are some references for normalization and also for denormalization that should be able to help guide you in your goal to strike that right balance in your database projects. Also, when you get the slides, you'll have some links to some free ebooks, and I would love to get some feedback on this presentation. And my contact information is listed here. And are we at this point, do we have any questions?
Yes, actually, we do. Thank you, Dr.
Okay.
Aaron, for such an insightful presentation. And we have a couple of questions. Debbie is asking regarding Rule 5. What if multiple column is to validate the entry? Example, confirm your email address.
Yeah, again, it all depends on your use case. I've seen that used quite a bit, for confirmation and validation, and there's certainly nothing wrong with that, as long as your use case says we are only going to accept a single email address for that validation purpose.
Okay, great. We have another one from Bawish. He's asking, does the normalization increase storage by creating more tables? Why is it still efficient?
Um, yes, you do. You do end up creating using more storage as you create tables, but because your table rows are going to be much smaller, it'll actually save you more space overall. Because if you had, say, for example, one really wide table and it contained a lot of data in that, it actually takes up more space than if you break it up into multiple small tables. It also makes your updates more efficient by being able to update just that particular value. It also ensures that your data integrity is going to be better, because instead of having multiple rows where I could have, I'm supposed to have the same value in these multiple rows, but one of them could be off, it could be mistyped or something, then, that's where having another table to set that would be more appropriate. Yeah, I'll
Yeah.
just close with another comment, is that when it comes to trying to determine the balance between normalization and denormalization, it's not an exact science. You see all the rules that are in there, but as a friend of mine is always kind of fond of saying, that in every situation it depends on what the use case is, what the circumstances are, and you're going to have to figure out what that balance is. There's no exact rule for that. But these are guidelines to help you in being able to strike that balance.
Thank you, Dr. Aaron, for sharing such an insightful presentation, and thank you, everyone, for joining us today.
All right, thank you.
Thank you, everyone. Have a nice day.